Okay, here we go. This is section 6.2. Now, section 6.2 and 6.4, the reason why we do those back to back is because they both deal with means or averages. 6.2 specifically is just focusing on one group. It also, like 6.1 and 6.3, introduces a formula that you can use to calculate standard error as opposed to what we did in chapter 3, which was the bootstrapping. It's pretty quick. The main things that you need are what is the sample size that you're interested in using, and then also it needs standard deviation. Which standard deviation, it's been a little while since we've seen that. Is if you're doing a population standard deviation, they use sigma, and that's it. Yeah, if we wanted to do this is about Major League Baseball players and how much that they are earning in terms of their salary. And if you wanted to do sample sizes of 30 and you knew that the standard deviation for just one sample was 4.7. Now, again, remember, standard deviation and standard error are two different things. Um, Standard deviation is how much variation there is within just one sample, and standard error is how much variation there is amongst like many samples. So we're switching standard deviation to standard error. And the way that we do it is by taking, again, just look at that little formula there up at the top right corner. You take your standard deviation and you divide it by the square root of the sample size, which would be 30. So it's pretty quick. Yeah, you should get from this 0.858. Again, for standard errors, I usually like to do at least 3 decimal places. I feel like that just gives a little extra oomph of accuracy. And B is the same thing, except that they want us to do, well, what if we were to increase the sample size to 70? What that's going to do is get our standard error to decrease to give us more accuracy, like a more narrow interval. Now, the big thing that's showing up at 6.2, and it's sort of been, kind of hinted at, or, you know, in that whenever you're going to use the normal distribution, you want your sample size to be large enough. And if you were doing like 500 people, 1,000 people, that's plenty. But what if you ever were doing a sample and this could happen where you're only able to get maybe 20 people in your sample or only 10. If that ever happens, then the shape of your distribution might not be as close to the normal distribution as you would hope it to be. So what they did is they invented something known as a T distribution. And actually, the individual's name is William Gossett, who came up with it. He's also famous for working for like Guinness Beer. But T distribution, and again, you can see there's quite a bit here, but I want you to mainly know that it's the same little formula. The S there is just standard deviation, so you can leave it as S or SD. But you primarily use the T distribution, which has an adjusted shape whenever your sample sizes are smaller. And here I'll circle it. Yeah, anytime your sample sizes are smaller than 30, you should consider using the T distribution. So like if you got 28 or you've got 20, yeah, you can use this, and the shape has been adjusted so that you can get your standard error, confidence intervals, p values, the normal things that we've been doing ever since like chapter 4, 5, and 6. And but what's cool is that the T distribution, although the motivation might feel to use it more for smaller sample sizes, it also works perfectly well for sample sizes of 500 or 1,000. So it's good. You use it for big stuff, you use it for small stuff. The only thing that it does require that's different than the normal distribution is what's known as a degree of freedom. There's probably we could maybe go off track with and by talking about degrees of freedom, but what I want you to do is think about degrees of freedom in the simplest way in this class is that it is a way to note what your sample was, sample size. But the -1, again, not to make it a super long-winded explanation, whenever they're doing standard deviation calculations or standard error calculations, um, there is a square root. There's a squaring and a square root inverse operation that happens. And the way that I've thought about it is that some textbooks would do -1 embedded in that calculation to help rescue some of like the accuracy. But for us in our class, I want you just to think about it as, hey, it's a way for us to let StatKey know, hey, here's what our sample size was. And if it's a t distribution, it's most likely because we're leaning on it for smaller samples. But that's it. That's all I'm gonna. That's as far as I want to go into. What's the meaning behind standard deviation? So let's do what we did in 5.1. Let's get acquainted with this new distribution. If we were actually, I'm gonna do the p-values first. That's what we did in 5.1 when we first introduced the normal distribution. And what we did, we said, well, it's still primarily going to be to help us do, p-values, right tail, p-values, left tail. And suppose we were doing a right tail, and they're not going to call it a z value. They're now going to call it a t value or a t test statistic because it's now with the t distribution. But what's going to be different is rather than just going and clicking the right tail and putting your value at the bottom, you're also going to need to put in there the degree of freedom. And so suppose we're doing a sample size of 15, which is the whole reason, the big reason to be using t distributions is that's really small, is that you would come here and note that the degree of freedom is 14. And then you would do the right tail, you would put the 2.3 down at the bottom. But let's try it. Let's go ahead and do it. So we're going to go to stat key. And I've got stat key right here. So it's going to feel a lot like the normal distribution, except right there it is right there. Right next to the normal distribution, click on the T. And immediately it's going to ask you for that degree of freedom. Again, I want you to just think of this is almost kind of like we're saying what the sample size is, except -1. So once you have your 14 in there, now you can do business as usual. Click like your right tail. There's the default p-value of 0.25, and that's where they want us to put down at the bottom where it says 2.145. Click it and change it to 2.3. And then you have the 0.019, which would be synonymous with us getting like a p-value so that we can reject, the null hypothesis. There is enough evidence. And that's it. That's how we use the t distribution to get p-values. But let's try another one. Let's do part C. Suppose we were doing a sample size of 50. Then the degree of freedom would be -1, which would give us 49. Now we're imagining ourselves doing left tail with a -1.22. So going over to the t distribution. So we got to change the degree of freedom. Let's first just like reset the plot, just blank it out. Right here where it says edit parameters is one way you can change the degree of freedom. And so you would get rid of that and change it to 49 and click OK. So there it is updated. You click your left tail. I already clicked my left tail. Boom, ready to go. And then right here at the very bottom where it says -2.010, change that to what they want us to, which is a -1.22. And again, the main one of the big main reasons we're going to be using the t distribution is to get p values, and that would be at the point 114. Now, the other thing we'll be doing, not just hypothesis tests, left tail, right tail, p value, reject, don't reject. We're also going to use it to get what our t star value should be. Now, remember in 6.1 was the first time that we saw where when we were doing our, I'm going to put it right here, but I'm going to take it off. Just we don't really need this right now. Where we were doing our confidence interval, uh, z star was what we would need to multiply to get either a 95 or a 99 or a 90 interval. And remember, the 95 was like 1.96. Okay, well, those two other ones, those the 2.576 and the 1.645, if we wanted to go wider, if we wanted to go more narrow. But the Z star today is a T star. And if you were doing 90, 95, 99, you would need to know your sample size, which we have it right here. It is for part A, which would then lead us to knowing our degree of freedom, which is 17. But to get the T star, we would need that 17 and also to know like how wide of an interval we want, which let's say we're doing a 90. So watch, we would go to, so it's a very specific value that you're multiplying against with the standard error. So I'm just going to erase this. And actually, what I'm going to do is I'm going to go to the home page. This is another way to not forget to update your degree of freedom. Is come back to the home page, and then I'm going to click on the T for the T distribution, and it'll ask me for the degree of freedom all over again, which right now we're doing part A would be 18 minus 1, which is 17. And if you're working on an example or a homework problem that's specifically about confidence interval, it's not just about the left tail. It's not just about the right tail. It's a two tail. We want the lower and the upper. So for these, you'll always click two tail. Now, as of right now, it's showing 95% interval in the middle, and we want to do a 90. So I'm gonna go ahead and click on it right here in the middle where it says 0.95, and I'm gonna change it to 0.90, which is a more narrow. So now I got the 0.90, and down there where you see the red, it's saying that would be what you need to multiply your standard error to get as wide as you want it to be, which would be the 1.74. You would do a minus version, you would do a plus version, but that is how much you would need to multiply to get that particular width. Okay, so all I was doing right there in example one was just a short little intro to how to use the T distribution, what we're going to be using it for. Let's actually go ahead and use it now in an example. Formulas are going to be given. So, this guy right here, how to get your standard error. They are also, here's a confidence interval. The example immediately tells you the sample size. This was a study to see whether eating dark chocolate would help with your vascular health, like your heart health. The sample was only 11 people, which is a big reason why they consider using the T distribution. And usually I throw like a true false in, it is something like, the if we're using sample sizes that are smaller than 30, accuracy becomes a concern. So we should use the T distribution. Like, yes, that would be like true. Yeah. Anytime you're doing less than 30, you're kind of a little bit nervous about accuracy. So you would use the T distribution. It's been invented to help you get good estimates for standard errors, confidence intervals, p values for smaller sample stuff. Now, So what they did in this study was for 2 weeks they gave the sample of individuals dark chocolate, and then they checked to see whether their vascular health was improved average wise, and you can see that the mean from the sample increase was 1.3 with a standard deviation of 2.32. Assume that the dot plot from the observed data is normal. So that's another thing that they're mentioning here. It's not something that we're going to be, doing a whole lot in looking into. But what they're saying here is that suppose that you don't have to put this in your notes, but that the 11 people suppose that they're roughly like bell shaped. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If it wasn't, then there'd be maybe a little chance that it could be like skewed or like biased. So they would recommend maybe using like the bootstrap method rather than the T distribution because shape wise, it's not going to pair up well with the symmetry. But so they're saying assume that it is, right? Assume that the normality assumption like is okay. So let's find a 90% confidence interval for the mean increase in vascular health after 2 weeks of dark chocolate. So the statistic, again, remember statistics are based on what was found out from the sample. And that was that there was a 1.3, that the mean increase was 1.3. The degrees of freedom would be 10 because we take the sample size minus 1. Now, if our goal, which is actually down here in part E, is to get an interval for the amount of increase in vascular heart health, for the eating of the dark chocolate, we would need a we would need to have the statistic, which we've already got, plus minus T star times our SE, which we'll get our SE in a moment, but the T star is something that we're not given. We are going to go to StatKey to get that. And if we're doing a 90% confidence interval and we know the degree of freedom, that's all you need. Just those two things. So we'd go to here. Again, I'm just going to go ahead and just wipe this thing clear and just right here go ahead and fix the degrees of freedom to 10. Click OK. And then once that's ready, now this is not a hypothesis test where we're doing p-value on the left tail or the right tail. This is a confidence interval, which we want the lower, we want the right, so we want the two tail. We want both sides of this. So we can interpret the lower to the upper. And 0.95 is not what we're interested in. We want 0.90. So go ahead and click on that and retype 0.90. Click OK. You should see down at the bottom 1.812. A negative because we were going to do a minus version, positive because we were going to do a plus version. But the 1.812 is going to be what we multiply whenever we get down here. Yeah, so it's going to be very specific as you go through your homework examples, but it'll be based on what your sample size is and what size interval that you're interested in. The good news is that the standard error formula is pretty quick. It's the standard deviation divided by the square root of the sample size. And I have a little rectangle around the standard deviation. It's the 2.32. And then the square root of 11. And you can double check it, but that should give you 0.700. And you don't need these extra zeros. So when you do your statistic, minus 1.812 times standard error, and that should get you your interval. Yeah, so it's definitely whenever you're doing this homework going to be, sort of the idea is that there's information that you're gathering bit by bit from part A. Um, part A, B, C, and D are like slowly just getting little bits of pieces of information so that when you get to part E, you can put it all together. But that right here is how much they're anticipating or predicting that your vascular health, measurement might increase if you eat dark chocolate for 2 weeks. Now, this right here is unit 4. In other words, like stuff for test 4. And notice that test 4, yeah, we're going to need still our template for interpreting confidence intervals. So we're going to start off with the level 95% confident. And then we want to mention whether it's mean or proportion. Today's lesson is about averages, about mean. And then the second line that I'm writing here is, what the variable is, the increase in vascular health. But just really just trying to lay out the context, 2 weeks of dark chocolate. And then the amount of increase is some number between 0.03 and 2.57. And that's it. Yeah, that's the t distribution. Um, the the next example is meant to be a just another super 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 similar example to that one. But I'll leave this one for you to try on your own. I mean, if you want, if anything, just pause the video now and try it. It's just use the one that we just did as a template. The only things that I want to mention is that your degree of freedom and your interval, like what I just have circled right now, that's going to be your degree of freedom, one minus your one taken away from your sample size, and then they want a 0.99. So here, let's at least maybe just do like the beginning of this one together. So it was a large sample of 1917. And remember, the t distribution is good for small sample sizes, like things less than 30, but it still works perfectly fine for big stuff too. And on this one, you would have 1970 minus 1. So you'd have degree of freedom 1916. So those two things are what you would put into the t distribution to get your t star. And I want you to try that one and see that you should get 2.578. And again, two tail, right? Since this is about confidence interval, you want to click the two tail. You want to change your degree of freedom to 1916. You want to change the middle to be 0.99. Here, I'll go ahead and do this with you. Yeah, we want to reset this. We want to, again, you can change it right here, or also if you just jump out to the home page and back into the t distribution, it'll ask you afresh for your degree of freedom. So now it's in there. Then you'll do your two tail. Now, if they wanted a 95%, we'd be done. Like down at the bottom, we'd have 1.961. But they want a 99, like a wide. interval. You put in your 0.99, and there it is at the bottom, 2.578. And that's what you would do, minus plus that number times your standard error. But the rest of the problem you should be able to do. Uh, I mean, go ahead and pause the video and try it. Use the last example, and then in a few moments, if anything, I'll give you at least the answers. All right, so let me go ahead and give you the results to this. I'm not going to work out every single little piece of it, but according to the sample, it was 13.10 was the average number of cell phone calls that were either made or received. That's per the sample. Then for the standard error, they mentioned up there that the standard deviation was 10.2. Then we know that the sample size was 1917, and that would give you 0.233. And then once you do here again, this is for you, right? You do the statistic, plus minus, 2.578 times your SE, and then you should have gotten, again, if we just keep one decimal, 12.5 to 13.7, and then we would end with we are 99%, and I'll let you finish that out. 99% confident that the number of cell phone calls that are made received by all cell phone users is between 12.5 and 13.7. All right. So again, I'll let you just, that was mainly an example for you to try independently with a few nudges from me. But I want to focus the rest of this lecture on doing a hypothesis test. And you'll see that there's also an extra one that you can try for yourself. That's, I think, pretty straightforward. But let's look at this one. Now, let me not ruin parts A and B. Read the prompt, find out what they're testing. You can write your HO, your HA. Notice that all the goodies that we're going to need are up at the top. Find your statistic, and then go ahead and do your SE. Right, just like 2 minutes to do this, and then I'll pause me, right, and then I'll do it. Okay, so it should be based on what they were testing, is that whether they wanted to check to see whether the average temperature increase for a man with a laptop computer on his lap for an hour is above the danger threshold, whether the average is above the danger threshold of 1 degree Celsius, which would be a right tell. The actual sample that came back that they had the men, they tell us up there that there was 29 men. And from them, what happened was an increase of 2.31. Yeah, you can see it up there. There's the 29 men from that sample, 2.31, which is definitely above the danger threshold of 1 if they're worried about, the quality or the impact, the impact it's going to happen on the sperm quantity and quality. Now, for the standard error, that's also something that we can do because they mentioned that the standard deviation was 0.96. And then calculate that, and you get your standard error. Now go ahead and try the next part as well too. Right. Again, there's going to be the next one that you can completely try on your own, but trying to do little nudges here. So we were doing the t distribution. Take your statistic, which is from the sample, subtract the null value, and you're going to get not what today's called we usually call it like the statistic. And then in 5.1, we're calling it the Z statistic because we're standardizing. And now today it's going to be called the T test statistic because it's going to get inputted into the T distribution. But your statistic was the 2.31. I mean, it tells us. And then the null would be the 1 from the null hypothesis. Then our standard error is the 0.178. Again, double check this, but you should get 7.36. Now, this is what we were doing at the very beginning of the lesson. You know, as long as you know that you're doing right tail and that the degree of freedom would be 28, again, because 29 minus 1, with this, and the t distribution, you can get your p-value. And business as usual. If the p-value is small, you can reject the null hypothesis. You can say that there's enough evidence for ... But let's go there and let's do it. Now, again, I tend to like to just go to the homepage and just re-enter the t distribution so that I don't forget that I need to do my degree of freedom, which would be 28. 29 minus 1, which is 28. And then we're doing on this one, we're doing a right tail test greater than 1. And don't immediately assume that that's our p-value. If we do say our p-value is 0.025, that's just the default. Down at the bottom is where we got to change, where you see my 2.048, change that to 7.36. Now, 7.36 is extreme. Remember, usually we would use that, back test 1, test 2, we would say anything that's more than 2 deviations from the center is extreme. And that right there is a very small p-value. It's in scientific notation. And anytime you see something in our Stacky that shows up scientific notation, it's because it's a super, super small number. Now, that is essentially what we're going to call just 0. Now, it's 2.6 e to the negative 8. Now, you would still take a screenshot of that and make sure to include it with your homework. But 2.6 e to the negative 8 is the same thing as 0. It's going to end up having 1, 2, 3, 4, 5, 6, 7. Yeah, so it's going to take like the decimal and move it like 1, 2, 3, 4, 5, 6, 7, 8 to the left, which that would be it in standard form. But for your homework, I mean, you can put that if you want, but I think what would be more helpful is just to say, just put that in your homework, like for the answer. Now, I can't remember. I believe in the answer key, I just put 0.00. So if you see this, you're like, wait, why does he have just 0.000? I went ahead and just rounded to 0. Okay, so just heads up. If you see scientific notations show up for one of your p-values, it's because it's really, really, really small. So doing a 1% alpha, we're good. Yeah, that's definitely 0.00000 is smaller than 0.01. So as we normally do, we can reject the null hypothesis. On this one, there is enough evidence or there is strong evidence to suggest or to support whichever word you want to use to support that the average, again, all you're restating is this, that the average is greater than one, or even better, just go back to what the test was, that the average temperature increase with the laptop on the lap is above the danger threshold of one. So don't skip out on the context. Make sure you get a good, healthy amount of what the study was about in there to support that the average temperature increase with laptop on lap for an hour is above 1 degree Celsius. Exclamation mark. This is like a health related study, and if they say something like this, they want to be as confident as they can. So that's why they're doing the 1%. Alrighty. Well, that's the main thing I wanted to do. Again, if you want to try this last one on your own independently, go for it. Just like pause the video. It's super similar to the one that we just did, and in a few moments, I'll just reveal what the answers are. All right, here it comes. So on this one, they did a sample of 30 teams, and the null was to see whether the average was less than 13, right? Penalty minutes per game. The mean number of penalty minutes per game for all teams is less than 13, which would be a left tail test. The sample came back with 12.2. The standard error, again, if you just follow the formula, should give you 411. The t-value, again, using just the stat minus null over SE. Again, if you put everything in there, yeah, that was provided up at the top, right? You should get negative 1.95. Since that was 30 in the sample, your degree of freedom would be 29. And again, using that it's a left tail, degree of freedom 29 and negative 1.95. I'll show that one here in just a second. You should get 0.03 for your p-value, which I'm going to let you write those out. It would be reject HO. There is enough evidence that the mean number of penalty minutes per hockey game is less than 13. And again, I'm just going to do real quick just going to wipe this out, change my degree of freedoms to be 29. Left tail. And then we have to change this to the negative 1.95. That's the p-value. That at 5%, at a p-value less a significance level of 5%, we'd be able to reject. Okay. All right. So again, these quick quizzes are meant to be for you. I wanted to always make sure to go through like all the little tiny, as much thoroughness as I can with the main examples. But that is it. I'm gonna go ahead and end the recording there. Again, we are slowly getting closer and closer to the end of this class, but still as usual, if you run into questions, let me know.